What is the true nature of reality? I mean, it is quite possibly the single biggest question humanity has ever dared to ask. And to answer it, we do something pretty uniquely human. We invent stories. You see, science is essentially just a series of stories we humans invent to try and make sense of a deeply complicated universe. We test our stories, we figure out what to keep, and we toss out the rest. But here's the catch. The more we learn, the more complicated and honestly, genuinely weird our stories become.
Welcome to This Explainer. Today, we're diving headfirst into one of the most famous, controversial, and often entirely misunderstood stories in all of theoretical physics. I'm talking about string theory. So is it the ultimate story of everything, the final missing puzzle piece, or is it just some hyped-up mathematical idea we should probably just chuck out? Well, to truly understand the nature of reality, we need to unpack exactly why we came up with it in the first place.
Chapter 1. Stories of the Universe.
Okay, let's dive into this. To understand string theory, we have to trace how our story of reality evolved as we zoomed in closer and closer on the world. I mean, we started with these wondrous, complex molecular landscapes, right? Then we moved down to atoms, which for a long time we absolutely believed were the unbreakable foundation of everything. That is, until we finally smashed those apart to reveal elementary particles, the true rock-bottom fundamental building blocks of everything in existence. Chapter 2. The Limits of Seeing. Now, reaching the level of elementary particles was monumental, but it immediately created a massive problem, because they are just unfathomably small. So small, in fact, that we essentially hit a physical wall. I want you to stop and think about what seeing actually is. For you to see anything, an electromagnetic wave, like a ray of visible light, has to hit an object and bounce back into your eye. Seeing is, quite literally, an active process of touching. You absolutely cannot see something without interacting with it in some way. And this brilliantly illustrates our ultimate catch-22. Normal electromagnetic waves, like the light lighting up your room right now, have wavelengths that are simply too big. They pass right over tiny elementary particles without even grazing them. So what do physicists do? They try using smaller, tighter wavelengths. But here's the issue. Shorter wavelengths pack significantly more energy. When these high-energy waves finally touch a tiny particle, they hit it so hard that they alter it. Just by trying to look at the particle, we fundamentally change what it's doing. We formally call this undeniable fact the Heisenberg uncertainty principle. It is the absolute bedrock of quantum physics. Basically, it dictates a fundamental limitation that prevents us from ever precisely measuring elementary particles. And look, this isn't just some mathematical technicality. It means the true visual nature of a particle is fundamentally hidden from us. When we look as hard as we literally can, all we get are these blurry spheres of influence. We don't actually know their true nature.
Chapter 3. The point-particle fiction.
So, you're probably wondering, if we can't accurately see or measure these particles, how on earth do we actually do any science with them? Well, we invent a brand new mathematical fiction. Physicists just decided to pretend that a particle, like an electron for instance, is nothing but a point in space. No volume, no size, just a tiny, indistinguishable point with a specific electric charge and mass. This framework, which is called quantum field theory, allowed physicists to treat those blurry spheres as precise, predictable points so they could actually calculate their interactions. And the success of this? It was absolutely astounding. Even though we know particles aren't literally zero-dimensional points, this fictional point story is so incredibly powerful that it predicts certain quantum properties of the electron with an accuracy up to 0.000000002%. I mean, that is just mind-blowing precision. It gave us the standard model of particle physics and, frankly, advanced the real-world technology we rely on every single day. Chapter 4. The Problem with Gravity. But as always, there's a dramatic twist. Just when quantum field theory seemed completely perfect, gravity ruined the plot. Think of the universe like a grand play. In quantum mechanics, the particles are the actors moving around. But in Einstein's general relativity, gravity isn't an actor. Actually, scratch that, it's not even a standard force, it is the stage itself. Gravity is the actual geometry of space-time. And describing geometry demands absolute precision. But remember the Heisenberg uncertainty principle? We inherently lack precision in the quantum world. So when physicists try to smash the story of gravity into the story of quantum mechanics by inventing a gravity particle, the mathematics just breaks down entirely. Chapter 5. Enter string theory. So the crucial point is, to successfully marry the stage of gravity to the quantum actors, physicists realized they needed a completely new story, a completely new framework. They asked themselves, okay, what is slightly more complex than a mere point? A string.
Imagine a violin string for a second. Depending on exactly how that single string vibrates, it produces distinct musical notes. String theory elegantly suggests that all our different elementary particles are just different modes of vibration on a single, fundamental string. And most importantly, one of those vibrational notes perfectly describes the carrier of gravity. Suddenly, boom, all the fundamental forces could be unified under one elegant concept.
Now, as you can imagine, the initial excitement and hype around this were huge. The idea spread like wildfire. But unfortunately, this theory comes with a lot of, well, literal strings attached. The biggest flaw? Much of the math just doesn't work in our universe with our standard 3 spatial dimensions and 1 dimension of time. To work out mathematically, string theory demands 10 dimensions. 10! So physicists have to do calculations and model universes, and then attempt to mathematically erase the 6 extra invisible dimensions to make it match our reality. And so far, no one has pulled it off. And even worse, 0 predictions from string theory have ever been proven in an actual experiment. No experimental proof whatsoever.
Chapter 6. Why Strings Still Matter.
So, a natural skeptic might ask, without any experimental proof, why do we even bother with it? Well, imagine for a second that you want to build a massive, state-of-the-art cruise ship, which represents our ultimate theory of quantum gravity. But right now, all you have are the blueprints for a small rowing boat, which represents string theory. The engines, the materials, the scale, they're obviously totally different. Yet, they are both fundamentally about things that float. By intensely studying those theoretical rowing boat blueprints, you can still learn the crucial fundamentals about buoyancy and fluid dynamics that you'll absolutely need to eventually build that cruise ship.
Now, what's really interesting here is that, despite its physical flaws, the pure mathematics of string theory are perfectly sound. The math works. 2 + 2 still equals 4. So theoretical physicists use it as this incredibly precious tool, a compass really, pointing us toward answers for massive mysteries. They use it to explore the mechanics of black holes, to tackle things like the information paradox, and honestly, it has led to the discovery of entirely new realms of beautiful mathematics. So what does this all mean for us? Well, string theory might not end up being the final theory of everything. But just like that fictional point particle we talked about earlier, it remains a highly useful story in humanity's endless pursuit of the unknown. Science is, for sure, a continuous process of refining our narratives, figuring out what works, and building on it. Which leaves us with this final massive question. If string theory is just our current blueprint, what will our next story be until we finally understand reality? Keep questioning, keep learning, and thank you so much for joining me on this explainer.